Good evening. My name is Byron Henderson.
My name is Faisal Ahmed.
Good evening. My name is Devin Luckett.
My name is Michael Fofley, and this is our refrigeration power cycle.
So the introduction, the refrigeration power cycle operates at a steady state using a refrigerant as working fluid to run the air conditioner. We use refrigerant 124 as our working fluid to formulate the refrigerator power cycle. And our project goal, the main goal of the project was to design a refrigerator system for a chemical engineering department newly constructed parallel parallel computing micro artificial intelligence center lab. Um, our proposed design is a hybrid hyper refrigeration power cycle that will be used to maintain several racks of computer nodes at a maximum temperature of 40 degrees Fahrenheit.
Understanding the design problem. To begin, we drew out our refrigeration power cycle shown in Figure 5 to identify what we have was known and what we didn't know. R124, shown in Figure 5, enters an adiabatic compressor where it reaches temperature 2 and pressure 2. The refrigerant is then cooled by an atmospheric heat exchanger, lastly throttled through an isotropic turbine where it expands to pressure 4. To increase the efficiency of the refrigerant cycle, the evaporator and condenser should be sized correctly and keys properly. Emissions from the process should not be released into the atmosphere because it is dangerous to the environment, ozone layer, and can cause global warming due to its porous in its nature. The formulas we use to solve our design or refrigeration power design cycle was the ideal gas law to calculate the volume, the mass flow rate to calculate the refrigerant cycle rate, the COP equation to calculate the coefficient CO performance, the work compression equation to calculate the rate amount of work done, and the work equation to calculate the rate of actually work, minimum work was required.
The next step of the process was to solve for the problem. So the first thing we did was illustrate the refrigeration power cycle as shown in Figure 5. And as you can see, as of now, our Figure 5 has all the values already solved for, but at first we didn't know any of these values. So the first thing we did was plot out for each state the different pressure, temperature, entropy, and enthalpy. And then after that, we use a Figure 2, our pH diagram, in order to get the values that you see in table 1, which is our thermodynamic properties for each of the different states. So after we illustrated out our refrigeration power cycle, then we had to make assumptions for our cycle to know what we knew and what we didn't know. Well, first we thought that we felt as if it was safe to assume that P1 equals to P4 and P2 equals to P3 due to state 4 and state 2 being an isobaric process. After that, we also assumed that it was safe that T1 is equal to 2,4 due to state 4 being an isothermal process as well. Isobaric means that pressure will remain constant, and isothermal means that the temperature will remain constant. And then lastly, we assumed that it was an ideal cycle, and since we know that it's an ideal cycle, it's safe to assume that we can use the ideal gas law. The ideal gas law is how we found our volume values for this cycle. And as you can see in Figure 4, this is what we use to make our PV diagram.
All right. In this cycle, we learned that the compression adiabatically causes a rise in temperature and work done. No heat goes out and work done on the system increases energy, hence the temperature increase. In isobaric process, heat is added to the refrigerant, while in an isotropic turbine, there is no transfer of heat. The refrigerant is expanded instead, and it flows through the refrigeration coils to a cool computer room by absorbing heat. With this information, we were able to comprehend and find the initial design values for every process of the project, while simultaneously having the actual refrigeration power cycle to look forward to it as well. In the cycle, we focus only on the ideal cycle and not the actual cycle. In addition to that, we also were able to compete all the objectives asked of us, which is to find the refrigerant circulation rate, actual work, and minimum work required. We were able to solve these values by solving for the initial design values first. We didn't find the efficiencies for the cycles because the information that we haven't learned yet.